Okay, now we're going to get into Chapter 7, which has everything to do with bonding and molecular structure. Get to build some molecules now. Okay, so when atoms or ions are strongly attracted to each other, we call that a bond, a chemical bond. And there are three general types of chemical bonds. The ionic bond, which we've talked about before, and that's just a force when ions of opposite charges are attracted to each other. So that's called an electrostatic force. We know that the ions can already be formed, or they can be formed from atoms by the transfer of electrons, and we'll talk about that near the end of the chapter. Ionic substances generally result from the interaction of a metal. Metals tend to give up electrons, and a nonmetal. Nonmetals tend to gain electrons and become negative. The metals tend to become positive. Of course, except noble gases, because they already have 8 electrons and they don't want any more and they don't want to give up any. Okay, so the second kind of chemical bond is a covalent bond, and this is from sharing electrons. If electrons are shared between atoms, those tend to be two nonmetals that are interacting with each other. So some examples: H2O, CO2, NO2, all kinds of different two nonmetals. And that's because since all nonmetals, there's not a balance, they're going to have to find out and figure out another way of getting the 8 electrons that they want to have to try to be like the noble gases. Finally, the third type of chemical bond is called a metallic bond. And this is where each metal is bonded to several other metals. In this case, what happens is all the electrons are kind of free to move throughout the three-dimensional structure. And this is what gives rise to the fact that metals can conduct electricity, and also the luster they have, because electrons are free to move around. We're really not going to focus in this class on the metallic bond, just kind of know the definition of it, but we're going to look specifically at covalent and ionic bonds in this chapter. All right, so why do atoms make bonds? This all goes back to our noble gases. The noble gases are very stable, they're very non-reactive, they have exactly the number of electrons that they want. They have a full shell of electrons, their full outer shell. So now again, this doesn't count the d electrons, because remember then, like let's say we filled the 3s and the 3p, and then we get to the 4s. The d's don't fill, the 3 d's don't fill till after we're in the 4th shell. So when we talk about the valence electrons, we're always talking about the highest energy level. So we're not necessarily talking about the d electrons. So noble gases have full s and p subshells. They're happy that way. They don't need any more electrons. They don't want to give up any electrons. They're just happy. And so it turns out that all other atoms tend to gain or lose or share electrons until they have those 8 valence electrons, which corresponds again to a full s and p subshell. So that's called the octet rule. So lots of atoms like to have 8 electrons. All right, now what we're going to do in this chapter is draw Lewis electron dot structures. So a Lewis electron dot symbol is just a symbol where the electrons are represented by dots. So if we look, we know how we can find the valence electrons. The valence electrons, remember, are the highest energy level electrons. So if we're in group 1, there's 1 valence electron. If we're in group 2, there's 2 valence electrons. Group 3 has 3. Group 4 has 4. These are the A groups. So so this would also be group 13, 14, 15. 16, 17, and 18. So these are the A groups here. But that we have the same number. So if you look at the A group numbers, the number of valence electrons are the same as the group number. So group 8A, 7A, 6A, 5A, 4A, 3A, 2A. All right, so 1 up till 8 valence electrons. When two nonmetals bond, we're going to mix it up a little bit, and we're going to start with nonmetals. I partly do this because we can get into the lab and do some of the structures a little quicker than we can. I kind of put the ionic bond later. Okay, so when two nonmetals bond, they share electrons. It's because they have similar attractions for electrons. So there's not one that's more willing to give up electrons, and so the only thing they can do is sharing them. And so, as we just said, that's called a covalent bond. So what happens is that atoms will share just enough electrons so that they have their noble gas configuration, in other words, so that they can have those 8 valence electrons, the octet rule. All right, if we start with hydrogen, hydrogen is the simplest example of a covalent bond, and actually hydrogen's one of the exceptions to the octet rule because we know hydrogen is in the first, let me use a different color, hydrogen is in the first shell, so we know for it to be full, to be like helium, it needs 2 electrons, and so it doesn't get all 8, it only needs 2. So two hydrogen atoms, here's a hydrogen atom and here's a hydrogen atom, and as they get closer to each other, they start to attract. There's the electrons are negative and the nuclei are positive, and so the electrons are attracted to the positive nuclei. Let me do it this way. The electrons start being attracted to the opposite nuclei. And so what happens is those electrons get shared between the 2 atoms, and they're kind of held in between. I think the picture's on the next slide, so it'll be a little more obvious. So obviously the positive charges repel each other, so that's one reason why they don't get too close to each other. But as these electrons are attracted to each positive, the electrons end up sort of being held in between them, and so they're attracted to both nuclei, and so that's what causes a bond. The attractive forces have to exceed the repulsive forces, and actually there's some higher types of bonding with quantum mechanics, like we talked about in the previous chapter. There are some higher types of mathematical models that talk about this, but we're just going to go kind of with the simple, straightforward bond, or the straightforward example, explanation, I should say. Okay, so here's what I'm talking about. So we have this kind of electron density. So remember, a dot kind of represents where an electron might be, and you can see that most of the electron density then is between the 2 nuclei. Here's my 2 nuclei, and all my density mostly between the 2 hydrogen, and that's kind of like a glue holding the 2 hydrogen atoms together. So the electron density concentrates between the nuclei, so the overall net attractions are attractive, and it's kind of like the glue that holds the 2 atoms together. This is how we can represent, using Lewis structures, what's going on. So hydrogen has 1 valence electron, and this hydrogen has 1 valence electron. So when they get stuck together, we show two dots, which is considered a bond. And so 2 electrons is considered a covalent bond. We can use either 2 dots to represent a bond. Sometimes we'll use a dash. So sometimes you'll see this. If you see a dash between 2 elements, that represents the same thing. It's a pair of electrons, and we call them shared electrons because they're shared between the 2 atoms. So this is a pair of shared electrons. And this kind of shows what the structure looked like. So each hydrogen actually counts both electrons for itself. So this hydrogen can claim those 2 electrons, and this hydrogen can claim its 2 electrons, since the electrons kind of end up they're around both atoms, they both can claim them. And so this is a way that hydrogen has now filled its outer shell, which happens to be the first shell. So once it gets 2 electrons, it's happy, and so that bond sort of satisfies that exception to the octet rule, where it has to have 2 electrons. So each hydrogen, in fact, has a helium configuration. It has 2 electrons. In a similar way, we can show a bond between a hydrogen and a chlorine. Now, chlorine is in the column 7A, so it has 7 valence electrons, and hydrogen has 1. So chlorine needs 1 more. Hydrogen, because it only needs 2, also needs 1 more. So we can show that here, the 7 and the 1. These are the Lewis structures. And when we stick them together, you can see that chlorine now has 8, hydrogen has 2, so they're both happy. Again, oftentimes you'll see it drawn like this. It just makes it a little bit neater to show the dash between elements, because it just kind of shows that they are they're bonded. So remember that a dash represents a pair of electrons, a pair of shared electrons. And then I still will put the dots here because these are the unshared electrons, and so sometimes we'll call this an unshared pair of electrons. And this is considered a shared pair of electrons. Electrons like to hang out in pairs, as we saw when we started doing electron configuration. So we've got 3 unshared pairs and 1 shared pair in this molecule. And so again, chlorine has 8, so it has the same electron configuration as argon. So this is considered a Lewis structure, and again, as I just said, we call these the pair in between the 2 atoms a bonding pair, or sometimes we call them a shared pair. And then the other ones are called lone pairs, or sometimes they're also called unshared pairs. So they mean the same thing, unshared or lone pairs, bonding pair, shared. And again, electrons like to stay in pairs, and that's what makes a bond. So for that reason, we can kind of see already in which groups how many bonds they tend to like to make. So hydrogen only needing 1 more electron, and then all of the halogens, fluorine, chlorine, bromine, iodine as well, they only need 1 more electron to fill their 7. They already have 7 electrons, so they tend to only make 1 bond. Now, it's not absolutely true. You'll see there'll be a few where they make more bonds, but you know, if you're kind of confused and not sure what to do, generally speaking, they like to make 1 bond. If they happen to be a center atom, we'll see a few examples. But similarly, oxygen with 6 valence electron needs 2 more, so it will like to make 2 bonds. Now, there is such a thing as a multiple bond, where they make 2 bonds to the same elements, but still 2 bonds. Nitrogen, being in the 5th group, wants 3 electrons, so it tends to make 3 bonds, and carbon and silicon like to make 4 bonds. So kind of keep that in mind in the back of your mind, because we'll be drawing molecules, and sometimes that helps. You can help double check to see if you did it right. But like I said, sometimes bromine, now phosphorus also likes to make 3 bonds because it's right below nitrogen, but it can make more, so it's kind of like some of these are exceptions to the rules that we'll see. But anyway, this is a nice generalization. As I mentioned, in most molecules described so far, each of the bonds is a single bond, but we can also have a double bond or a triple bond. So in a double bond, you can see here that 4 electrons or two pairs of electrons are shared between the same element. So this would be a double bond, and here represents, this is usually how we'll draw it with the bond between the elements. It's a little less messy than drawing a whole bunch of dots, but remember every line represents a pair of electrons. And yes, we can have triple bonds as well. So a triple bond is where 3 pairs of electrons are shared between the same atom. So here's, this is acetylene, so it's got 3 pairs of electrons shared between these 2 carbons, and so that's considered a triple bond. You can't have more than a triple bond, single, double, or triple. Now, we have something called a polar covalent bond. So covalent, again, means sharing. Polar has to do with, if you think about the Earth, where are the poles? The poles are at the 2 extremes, so there's kind of a difference between them. So a polar bond is one where there's a difference between the 2 ends of the bond. So a polar covalent bond is one where the bonding electrons are not shared evenly, and the electrons spend more time near one of the atoms than the other atom. So let's look at some examples. So a hydrogen-hydrogen bond would be considered nonpolar. Why is that? That's because the 2 atoms on either end of the bond are the same exact atom. So if they're the same, that means that they're sharing the electrons equally because they each have a similar attraction to the electrons. Remember, we talked in the last chapter about electron affinity. And some atoms, like electrons, or pull electrons tighter to itself than other atoms. But if the bond is between the same 2 atoms, then of course they have to share them equally. It's almost like a tug of war. So if one pulls harder than the other, you're going to be unequally sharing them. But if they're the same identical strength, they're going to pull evenly. So this is considered a nonpolar bond. But if the atoms have different electron affinity, then they're not going to necessarily share these electrons equally, and that leads to a polar bond. So OH is considered a polar bond. O has a very high electron affinity or electronegativity, which pretty much is nearly the same thing. Hydrogen has a pretty low electronegativity or electron affinity, and so they're not going to share these equally. So if you look here, this sort of shows electron density. Electrons, you can see, are it's much more pulled over here toward the oxygen and a lot less density over here by the hydrogen. So what this leads to is an unequal distribution. The pair of electrons are closer to the oxygen. I know they don't look closer, but because the density is more around the oxygen, it means that the electron density is closer to the oxygen. And since electrons are negative, this puts what's called a partial negative charge on the oxygen. It's not a full charge because oxygen didn't actually steal the electron from hydrogen. They're still sharing, but it's partially negative because it's a little closer to the oxygen than the hydrogen. And then that means that the hydrogen is partially positive. This is the little delta sign. It's the lowercase delta sign in the Greek alphabet, and so it just means it's partial or change in, but it's partially positive. So the hydrogen is partially positive, the oxygen is partially negative, and this is called a polar bond. It's still covalent because they're still sharing electrons, but it's polar. Whereas a carbon and a hydrogen bond tend to be nonpolar. So you can see that the electron density is a bit more evenly shared between them. Now, carbon actually is slightly higher in electronegativity than hydrogen, but not enough to make a big difference. So we don't really see a polar bond for carbon and hydrogen. Okay. Yep, so I already talked about that, partial negative, partial positive. Okay, So as I talked about, electronegativity is very similar to electron affinity. So affinity. So it's how much does an atom pull electrons toward itself? So it's a measure of the ability of an atom in a molecule to draw bonding electrons to itself. So the higher the electronegativity, the more the electrons are attracted to that atom. In general, very similar, we talked about this in the last chapter, if you have your periodic table, electron affinity and also electronegativity increases as you go up the periodic table, because the smaller you are, the easier it is to attract electrons. And then going to the right, because they already have so many electrons surrounding them that they want more electrons a bit more readily. You know, these metals over here are more willing to give up an electron than to accept an electron. So electron affinity increases as you go up here. Now we don't really include the noble gases. So fluorine up here at the upper right hand corner has the highest electronegativity of all the elements. And then I think it's francium down here is one of the lowest. There's a scale actually developed by Linus Pauling, a scientist, back in the beginning of the 20th century. He assigned the value of 4.0 to fluorine, which is the highest, and then he looked at, so actually cesium was assigned 0.7, and all the others were ranked kind of in value to each other. So here's an electronegativity chart. I believe I also have one in Canvas that you can print off, but the value under here is the electronegativity. So you can see fluorine's very high, oxygen also very high, chlorine and nitrogen are also very high. So it's kind of up here on this right hand corner, they're very high, and of course down here at the bottom they're very low. There's some variation, but you can kind of notice the trend. So one thing we can do is to determine if a bond is polar or nonpolar is to look at the values of the different electronegativities of the two atoms that are bonded to each other and subtract them and then take the absolute value. So in other words, you don't want to compare negative numbers. You just want to know the difference between them. So you always take the biggest minus the smallest, whatever order they're in. So take the positive of it. That's absolute value. And so if you find the difference, what that does is tells you how similar they are to each other, right? So if the difference is small, so let's look at an example here. If I said 2.5 and hydrogen's 2.1, I got those off the previous slide, the difference between them is 0.4. So anything less than 0.5 we consider nonpolar. I will say that sometimes different books have slightly different values for these cutoffs. I think actually the OpenStax textbook actually says less than 0.4, but I tend to want to include 0.4 in nonpolar. So for example, if the difference is 0.1, 0.1, 0.2, 0.3, 0.4, then we consider what that means is that these two elements are so similar in their pull on electrons that they're going to be, it's kind of like they're evenly matched in a tug of war. And so one atom doesn't have more of the electrons than the other. So we call that nonpolar. And again, like I said, some books might call 0.4 polar and some don't. I'm just going to go with 0.4, anything less than 0.5 being nonpolar. If the difference is larger, meaning equal to or greater than 0.5, then the bond is considered polar. So an example there would be OH. So OH is 2.1, O is 3.5. The difference between these is 1.4. So we're gonna put that into the into the polar category. So anything equal to 0.5 or greater than 0.5, we're going to consider polar. And actually, if we look at the whole spectrum, we can actually look at everything. And so if the difference exceeds, and again, this changes with different books, either sometimes they'll call 1.8, sometimes they'll call it 1.9, some books will say 2.0. So within this range, we're kind of go with 1.9. We consider that actually ionic. So for an example here, sodium and chlorine. So sodium has an electronegativity of about 0.9, and chlorine has an electronegativity of 3.0. So if you take that, you find the difference between them is 2.1. Again, remember absolute value. So 3 minus 0.9 is 2.1. We would consider this ionic. And what does that mean? Well, the difference is so great between these two. Chlorine wants electrons so much more than sodium does that, in fact, it's like a really uneven tug of war. Chlorine actually steals the electron away from sodium. So eventually sodium totally loses that electron and chlorine totally gains it. So here we have a full-on difference in charges, whereas where we saw earlier the oxygen, this is not strong enough to actually pull the electron away from hydrogen, but we get a partial charge. So that's kind of our spectrum. We have something that shares, like the carbon-hydrogen or just a hydrogen-hydrogen bond. Of course, if they're identical to each other, the difference is 0. And so with a difference of 0, they're obviously sharing them exactly equally. So we consider anything under 0.5 to be nonpolar, anything between equal to 0.5 and up to about 1.9 to be considered polar, and then anything above that is usually considered ionic. Of course, there are a few exceptions, but that's a really good trend, or really good guidelines to use. So here's some examples. So they're very similar to what I just showed you. So you can see here, chlorine, a bond between two chlorines is the difference between them. They're each 3, but again, so that's pretty high. They're both electronegative, but again, the difference between them is 0, meaning they're so similar to each other that the tug of war goes nowhere. So in fact, all the electrons are shared very evenly, equal sharing. And so if you look at these colors here, the fact that this is all green means that the electron density, or the negative charge, is kind of evenly distributed among the whole thing. If you look here at the hydrogen-chlorine bond, chlorine being 3.0, hydrogen being 2.1, again, the difference is 0.9, and so that's an unequal sharing. Chlorine having the high, so the written opposite, so that you could see the absolute value, but chlorine, the one that has the higher number, will be partially negative, and the one that's the smaller number will be partially positive. And in this picture here, you can see where it's more red, it's more negative, and where it's blue, it's more positive. So there's not an equal sharing here in this molecule. And then, like I just showed you, chlorine has a 3.0, sodium has a 0.9, and so the difference between them is 2.0, which is such a great difference that, in fact, it's ionic and they're not sharing at all. So equal sharing, unequal sharing, non-sharing. And you can see here the chlorine has all the electron density near it, and the sodium is positive, so not even. So the only reason why they're bonded is because the positive and negative are attracted to each other. There's no sharing at all between the elements. So obviously, the greater the difference in electronegativity, the more polar the bond. In fact, it can get to ionic. Okay, so the important thing about a polar covalent bond is that now we have, because we have some positive character and some negative character, what's going to happen is that the molecules are going to be attracted to each other. So the bond, the molecule itself is called a dipole. So just like our Earth has two poles, the dipole has two ends, as we saw, a negative end and a positive end. And this is a stupid picture because most everything I've ever seen calls negative red and positive blue. But anyway, they decided to, this picture decided to shake it up a little bit. But anyway, the side where the chlorine is going to be more negative. We can measure the magnitude of a dipole. Sometimes it's called a dipole moment, and the bigger M is, the more polar it is. But here, like I was saying, so the polar molecules like to align themselves. So the negative charge, the negative end of one molecule is attracted, even though it's not a full-on charge, they're still attracted to each other. So they kind of line themselves up, and they're attracted to each other. And this is what sort of helps stick molecules close to each other. So polarity accounts for many properties of liquids and solids that we'll look at in future chapters. It's one reason H2O, I'll show you that. We'll talk about that later, of course, but H2O has the oxygen is more negative, the hydrogens are more positive, and so in fact it's the hydrogen bonding in water that causes water to have such a high boiling point for the size of a molecule it is. And actually the only reason why life is on Earth, because of this strong attraction between them, so polar bond.